So last time we were discussing state feedback control. So the idea behind state feedback control is that if we don't like the location of eigenvalues which correspond to the response of the system, then perhaps we can change the response of the system, or equivalently we can change the location of eigenvalues. So we can change the location of eigenvalues to our desired location. So can we do this for every system? Well, we have seen an example in that we can just use the state feedback control for a simple steering model of a car, and we can use the state feedback control to place the location of eigenvalues at our desired point. And then we saw, can we do this for all cases? We had this analysis tool called controllability, state controllability. So in state controllability we check if we can assign all the eigenvalues to our desired locations, or it is called pole placement or eigenvalue assignment. So to see if we can do this arbitrarily, we need to check the controllability. And for controllability, we know that we have to construct a simple matrix which is B, and the next column is AB, and the other next column is A square B, and it goes on until A raised to power n minus 1. So this was a very simple example in which n was 2. N is the dimension of a matrix, which in this case is 2. So of course we will only go to B and AB, because we will not have a square B here. So this controllability matrix we constructed, and we saw that both, let's say, rows or both columns are dependent on each other. So basically if you multiply the first row with 0, you will get the second row. Or otherwise, if you see that the first column is exactly the same as the second column. So the rank is 1, which means the independent rows and columns are just 1. This rank is not equal to 2, which is n, the dimension of a matrix. So the system is not completely state controllable. So what can we do in this case is we can only assign one eigenvalue as at our desired location, and we cannot place the second eigenvalue at our desired location. So here we see another example. This is another very simple system. In this case, again, n is 2. We see that n is the dimension of a matrix. So the a matrix is 2 by 2. So the n is 2. And well, does this look like a Jordan form to you? Because it exactly is Jordan form. So it has two zeros at the diagonals, and then there is this one at off diagonal, at the off diagonal position. So this system is, let's say, it has two eigenvalues, because we know that the eigenvalues on a Jordan block are on the diagonal. So it has eigenvalues which are at 0 and 0. So we know that the system is not stable. So the first question was, is this system stable? Of course it is not stable. Well, we know that the second equation does not come, let's say, into the picture of controllability or instability or state controllability. So we only need just the first equation, which is x dot is equal to ax plus bu. So this equation is useful. The second equation is just given for the sake of completion. So we see that, is the system stable? Well, of course it is not stable in the open loop. Can we stabilize this? Well, of course we can stabilize if we use these inputs. Well, then can we stabilize it using only one input? And if we see that the cost of first input is 1000 rupees, the cost of second input is 2000 rupees. So if we have to stabilize this system, which is the cost which is the minimum cost to stabilize the system? Is it just 1000 if we are able to stabilize it using only on the first input? If we can stabilize it using only the second input, then the cost would be 2000. But if we need both inputs, then of course the cost is going to be to 3000, which is 2000 plus 1000. So how do we check? Well, we check first with just u1. If there is u1 and there's no u2, we will only have first row in B, because u2 will be 0, so the second row of B will not matter. So we can delete the second row first, and that will give us the controllability solution for first row only. And the what we can do is we can check if the system is controllable with only first input, if it is controllable with only second input, or if it needs both. So I leave this very simple exercise to you, and all you have to do is just for the first controllability question, you have to delete the second column of let's say second column of this B matrix, and for the second time you have to delete the first column of the matrix, and then for the second time you don't have to delete anything, you just have to calculate the state controllability for the whole system, and then you will end up answering what is the cost to stabilize the system. So this is a very simple example which tells us how this controllability helps us in design. So this helps in examples like, for example, if you have an airplane and you have multiple inputs, which inputs would you have to use? And for example, if I ask you, not in terms of cost, but in terms of uh, fail safe, let's say, application of the mission. So in some missions we want that no matter which actuator fails, we should always be able to complete our mission. For example, you know that if one engine of a passenger jet fails even at the takeoff, it should be able to take off. So it is designed in such a way. So we need to design an airplane in such a way that even if one of the actuator fails, so one of the actuator means U1 is available. If the second actuator fails, or if the first actuator fails, then it means only U2 is available. So then this tells us if the system is controllable with the first input only or the second input only. So then it will tell us how critical is our selection of actuators. So we should always have some extra actuators because they may fail sometime.